Okay, for those of you who don't know me, my name is Damien Gray. I am a laser optical engineer at Vulcan Labs. For those of you who really know me, you know I just changed jobs about 2 weeks ago because my company got spun off. That means I actually get to tell you about what I'm doing instead of saying, oh, I'm doing this sort of weird thing with cRIOs and this is how I optimize them. I'll have a video at the end of the actual thing, but to make a long story short, we make metal 3D printers. So I have a picture at the end, or I have a video at the end. And anyway, okay, so I'm going to talk about how I optimized an FPGA that went from 10x not fitting in the FPGA down to about 90%, met timing requirements at 120 megahertz, and even kept most of my hair. So, quick overview. Before you start, I'm going to explain what the problem I was facing was, and then go through all the progressive things that I did to make it slowly better, and then I'll take questions. So, this is very important. You are going to be compiling FPGAs a lot. And some of you might say, well, I can just, use the cloud compile here at NI. Well, if you have a fast processor and an SSD, you can beat the cloud compile by a factor of 2. So compiling in 15 minutes versus 30 minutes or 10 minutes versus 20 minutes is a big deal when you're iterating a lot. So I would recommend getting an SSD, and that actually is the thing that makes the biggest change, is the SSD, because there's an awful lot of file access. So get an SSD, get a fast processor. Okay, here's what I started out with. I am doing a 10-axis motion control at 100 kilohertz. This is a 2-axis XYZ Galvo system with kilowatt lasers. So we're doing power and positions. Okay, so originally I had set it up so that the vector generation was done at our main controller. They just said, okay, draw these vectors. And the SCurve Generation was being done on an RT processor on a 9066 controller. So that's one of the Zinc controllers. And then the data, and then that was being dumped down to the FPGA to get clocked out in a deterministic fashion. Well, turns out that little 1-long arm processor, actually it's a 2-long arm processor, it wasn't fast enough to generate the S-curves. It just couldn't do it. It couldn't keep up. So what we did is we moved the SCurve Generation into the FPGA and to speed it up. And so the RT side of the business was basically just coordinating things. It wasn't actually doing a whole lot. And this is what happened. I just minimally modified it, just to barely get rid of all the things that an FPGA couldn't do, and tried to compile it. And it didn't work, as you would expect. But I want to emphasize that if it does work at this point, you're done. There is no reason for you to go further. If once you've met your goals, you've met your goals. I mean, if in the future you have to do something else, then it might be worth going through everything we're doing. But when you meet your goals, you need to stop and go on. Your job's done. Okay, so first thing you do, and this is probably going to be your biggest problem because it's going to require a lot of thought and probably a major amount of refactoring. Replace all your floating point with fixed point and integer stuff. FPGAs really don't speak floating point. They like integers. That's what their base language is. They do integer multiplies. They do integer adds. They don't do divides very well either, but we'll get to that later. So what you have to do is go through your entire process, figure out how many bits do I really need right here, and if I multiply these two things together, it's going to double the number of bits that I have. If I add them together, it's going to add a bit. So as you do math, the amount of bits you have gets steadily bigger. Unfortunately, as the bigger the bits there are, the longer it takes to multiply or add or anything else. So your goal to make things fast is to try to keep the number of bits you've got on any one number down as low as possible. You will have to think about it. And it will take a while. So don't sell this short. It's not going to be a trivial, quick, do it now thing. But this will set you up for everything that comes after that because, like I said, FPGAs talk in integers very, very well. And if you've got the integers, then the rest of the stuff I'm about to show you becomes a lot easier. Next thing you can do is boost your clock frequency. I needed 100 kilohertz output frequency, and that gave me roughly at the 4 gigahertz, that gives you like 40 gigahertz. That gives you 40 megahertz. My brain right here. That gives you about 400 clock cycles per point. I did some quick analysis and stuff, and that just wasn't enough. So I had 20-bit output resolution, so I had to do some fairly high resolution stuff. And I was doing approximately 16 math operations per cycle. So, you know, you do the numbers here. Most things take as many clocks. If you use the standard addition multiplication, it takes as many clock cycles as there are bits to get it done. That's the standard Cordic algorithms. That's still better than, you know, doing floating point, but it did the math, and it just couldn't be done. So I boosted the thing up to 120 megahertz, and then I could pull it off. FPGAs will go to 480, 400? I'm trying to remember.
How fast is they can be compiled?
Yeah, I think they should.
Limited by compile a two of change based on the you're on.
Yeah.
240 megahertz, probably not going to get any higher than that.
Yeah. Well, the nice thing also is that you can compile different parts of it at different frequencies now, and that's really useful if you have to do for certain things. I ran into that. I use that later on. The next thing you can do is do less. This is an SCurve generation algorithm. Well, it's an iterative. It's basically an iterative motion calculation. And so your distance is, you know, distance 0 plus velocity times time plus half acceleration time plus 1/6 jerk times t cubed. Well, at each one of those things, you're having to compute time squared, and time cubed, when in reality that time is a constant because you're at a fixed interval, and so you can just throw it all away, rescale your velocity, acceleration, and jerk, and do much less work. And you know, that's both less time, less operations, and less fabric. So it's well worth your time to look at things like that and see what you can do. And there's a wealth of algorithms on the web for almost any sort of FPGA work. You know, if you want to do a PID loop, for example, you can go on the web and find very simple algorithms that do essentially this as well. So you don't have to dream them up yourself if you don't have to, unless you're doing something really custom. But all of this stuff is very easily available. Okay, this was the one that really killed me. Divides take a huge amount of both time and fabric. Destroy them, get rid of them. So anything, divide, quotient and remainder, inverse, all of those things do divides under the hood, and all of them will kill your time. One thing you can do if you're dividing by a constant that helps a lot is just invert the constant, bit shift it up, you know, 10 bits, 20 bits, whatever, and just do a multiply. And then bit shift it down the other way when you're done. That works really well. And it's a way to do a divide and actually really do a multiply. Here's a couple of things I did too. You know, I was using the quotient and remainder is something I use a lot in my normal LabVIEW code. And there's a couple of things here I did, like I was detecting odd by you know, doing a quotient and remainder divide by 2. And but on the FPGA, I just did the single rotate. And in fact, in this particular case, I needed to divide by 2 anyway, so it was a win-win. I both found out whether it was odd or even, and I divided by 2 all in one swoop. Fell swoop. So sometimes you get lucky. Okay, use memory for arrays. Most of the FPGAs that NI cells have memory blocks, and arrays themselves just, I mean, if you just instantiate an array in your fabric, it just sucks the fabric dry really fast. I mean, if you have more than like 5 or 6 elements, it starts to just blow up in your face. However, memory, on the other hand, is essentially free space. I mean, you can access it. You will need to access it. I mean, it's basically like pointer arithmetic. You access whatever element it is, but it's a predefined block at the beginning. You define how much your maximum you think you're going to need, and then you just use it, whatever it is. I've used them for buffers. I've used them for FIFOs. FIFOs are actually a good way to use to create arrays, because almost everything you're doing in an FPGA is some sort of serial piping data from one place to another, and a FIFO gives you a way to handle that without having to explicitly generate an array and take care of all the pointers and everything. And I've fit some pretty large arrays and stuff into my FPGA memory. Of course, 9066 has a fairly large amount of memory. It's one of the reasons I bought it. It's also got a ton of both DMA channels and DSP chip blocks, which I use extensively as well. Okay, another thing you want to do, oh man, those colors didn't come out very well, is avoid arbitration. Arbitration is if you've got an array and you're accessing it, if you have two things that are trying to access the same array at the same time, the same memory block at the same time, you have to arbitrate as to which one actually gets it. And that arbitration code takes fabric and it takes time. So try to design your algorithms so you don't have to have arbitration. One of the things I had to do was I was doing a two-dimensional linear interpolation for a correction table for these galvos. This correction table is basically a bilinear interpolation of galvo coordinates, so the number I would actually send to the galvos mapped onto where it was on where the laser was hitting on the part bed. And so that's just this big 65 by 65 table. Well, to do any one of those bilinear interpolations, I needed the 4 adjacent points. So instead of storing that as a single contiguous 65 by 65 array, I stored it as 4 separate arrays that were kind of put together into this pattern you see here. So for any one point, I had to figure out where in each one of the 4 arrays to go, but I'm only pulling 1 point out of it. So at that point, I can pull all 4 points out at once without having to worry about arbitration of pulling individual ones. And so I get a parallel action instead of a serial action, and I save myself time and I save myself fabric. However, I did have to do a little logic to get it done. But it worked beautifully. Okay, reduce your front panel controls. Front panel controls take fabric and time, and you're usually better off using something else to do it. I like using a DMA buffer for this, so DMA from the RT to the FPGA. And in this particular case, I've got a very, very simple command loop, which it just sits there and waits for something to come out the FIFO, and when it gets the first element out, tells it what command it is. It's just a simple number, and then the rest of it is just a string of numbers that then get interpreted however that particular command is. So here is what first find the start a packet and then the get the command. So this is what the fetch command go to new state VI that from this previous one. So it's have it here. Oh, there it is. Yeah, so if I go to the wait for command state, it would just be a VI sitting right here, and that's what the guts of it look like. And the output is simply the new state, which would then take you to the next state, which then executes, which then reads whatever else it needs to off the FIFO and executes the command. And I use this to initialize things like the correction tables and PID parameters. And actually, I used a similar form of it, not this one, but a little more complex form.
But didn't you say that you wanted to eliminate all the front panel control?
Yes. That's not a front panel control. That's a sub VI. That gets compiled into nothingness.
Have you looked at the register bus stuff at all from cRIO?
No, I have not.
It's actually for like very similar purposes. So this is probably better from a resource perspective. Frankly, but if you wanted a standardized way to do this, just using the initialize the register bus.
Okay.
I bet it's almost the same thing.
This was really easy to do, and I'm still using this. Yeah, this is simple and easy to do. Okay, now we get to the meat of it. So I'm generating SCurves. That's what I'm trying to do, which means I'm generating some math, and the equations I gave you earlier were the actual equations used in the SCurve, or some of them. Now, the standard high throughput math uses Cordic algorithms. Cordic algorithms have been around, since the 30s, I guess. The original HP calculators used them, and that was how they were so fast. But Cordic algorithms also have the advantage that you can do as many bits as you want with them. It's basically each successive approximation gives you one more bit. The downside is it's 1 bit per clock cycle. And for me, that was kind of death. So I tried them, and they didn't work for me. So I went to DSPs. The DSPs at root are simple multiply adders. So they do a multiply and then an add, all in essentially a single operation. Depending how many bits there are, they can take somewhere between 3 and 8 clock cycles to execute. But in that time, you've just done a 48-bit operation. So way faster than Cordic algorithms. And the Xilinx, on your palette, there's these Xilinx IP nodes, and they have a lot of higher level functionality that will efficiently create mathematical functions for you exactly what you want. So if you want, a 43-bit times a 24-bit operation, it will generate that in the most efficient way it can using, and you have a choice in their IP nodes too. You don't have to do a DSP. You can also do, say, Fabric or use registers or something. Anyway, but the DSPs are definitely the most efficient and fastest way to do this. However, they have some problems. One, their documentation is, shall we say, poor. Basically, NI's documentation points you to Xilinx documentation, which is basically written for VHDL programmers.
So like, I'm using you because I don't want to be VHDL.
Exactly. But you can kind of work your way through it. And the other thing you have to be aware of is if you use the DSPs or the Xilinx IP nodes, when it comes time to upgrade your LabVIEW to get that next version and they give you a new Xilinx compiler, you've got to go back and not just recompile them, but reconfigure them, because LabVIEW loses the recipe. So I would highly recommend that if you use DSPs or IP nodes, and if you need speed, you really should, because they are really fast, write down right next to them on the block diagram what they are, how you configure them. Anyway, whatever it takes to give you a nice thing. And yes, I have complained about this vocally more than once. Hopefully it will get fixed in a future version of LabVIEW.
Now, to Xilinx credit, though, the documentation isn't bad because there isn't enough.
Mm-hmm. Xilinx, if I was a VHDL programmer, it would be great.
It's like 200 pages.
Oh, yeah, absolutely. Absolutely. It's
I'm sure it's great.
Well, the biggest problem with it is it's more of a reference manual than a user guide.
Yeah.
And if you know what you're doing, it's all there, and but there's no, okay, new user, this is where you start. Anyway, so just to give you a little flavor of it, this is what you get for configuring a DSP. And I will be fair and say this is the complex DSP you get on the 9060, so on the new Zinc processors. There is a DSP 48E, which is a little simpler, but you've got control over almost absolutely everything about what multiplies and what adds, and whether it's an add or a subtract, whether it's signed or unsigned. About the only thing you don't have control over actually is the bit depths. They're fixed by the actual DSP itself. And LabVIEW implements these as fixed point integer and fixed point width, both the same. And the reason it does that is because that's the only way LabVIEW has of specifying a specific number of bits. And the FPGA will actually, compile 25 bits, not 32. So you can save space doing that kind of thing. So you can actually, slowly grow things as long as you're using fixed points, and it will take care of it properly. But I'm not going to try to explain all this. Just it's a lot of stuff. But once you've stared at it for a little bit, it becomes a little more tolerable, and you can actually figure it out. The only thing I will mention in passing is these registers. Registers are basically ways of blocking your code into things that the compiler can then only has to meet timing on the space between the two registers. So if you don't meet timing, say you're trying to run at 240 megahertz, you can go in and turn on a couple more registers to block your code into a couple more blocks. You can do the same thing in your LabVIEW code by putting feed-forward nodes in. It basically inserts another register. But the downside of that is every time you do that, you have to iterate over the code one more time to get it to work. A hidden gotcha of these DSPs, they don't work in one pass. You have to put them in a loop, and you got to loop them at least as many times as there are registers between the input and the output. So your standard DSP is going to take you, like, if it's pretty basic, it's going to take you 3 cycles to actually do anything. So you have to put it in a timed loop it 3 times, and the output will give you, and then you'll get it.
So it's like a 4-bar handshaking that just runs this many iterations and take the output and the output?
Yes, you could do that. But DSPs also have a couple of, this little PC out here. There's a PC in someplace over here. Where is it? Trying to find it. Anyway, there is a PC in as well that basically allows you to, I think it either the A or the B or the C, where's the C? There it is. Can all be directly linked to the next DSP.
PCN is directly below the register.
Yeah. Oh yeah, there it is. Okay. Well, PCN basically, you can see it bypasses all the input registers and just directly adds to whatever's there. So you can use the PCN to kind of get PC out and PCN to kind of gang things together and get faster performance. Okay, I need to speed this up.
Did you just like try this and it works? Like...
How did you find out? Yeah, I was gonna ask that.
Yes. This was my first attempt right here. I had to tweak it a lot. This is the actual bilinear interpolation routine. So it goes in. It's got all the. It's got the numbers. You can see these fractions here are, for those of you who've done bilinear interpolation, there's a fraction between each of the points, and that's what those fractions are. They're the fraction that has been bit shifted, and then it's just adds and multiplies going through. And this thing, the bilinear interpolation, this thing executes in 5 clock cycles, so it's fast, and it'll give me 18-bit accuracy, which is exactly what I wanted. Anyway. Okay, here's a multiply node. So if you want to do a multiply, you could also, instead of going through the whole DSP thing and trying to figure out, these things are a lot more accessible. Unfortunately, they don't work on Windows 10. So just a warning. I was reliably informed at the Architect Summit that would be fixed in the next version of LabVIEW, which means I'm going to have to go through and recompile everything. But
Oh, we're having virtual machines.
Yeah, we're having virtual machines.
It's not NI's fault, by the way.
What?
It's not NI's fault.
Windows 10 Windows 10 compatible.
To be clear.
No.
To be clear, the Xilinx compiler doesn't support Windows 10.
It has since 2016.1.
The version we're using doesn't support Windows 10.
And it's 2 years old.
Development cycle, that's about as fast as you can get with yearly releases. So.
It is being fixed. It is being fixed. Hopefully it'll be fixed before I'm forced to go to Windows 10 at work. Anyway, so here's your multiply node configuration. Here you just have to say, is it signed, is it unsigned? You type in bit width. The multiplier construction there, use mults. Use mults actually uses the DSPs. You can also use fabric if you want to, depending on what you happen to have a surplus of on your particular thing. And you can optimize it for speed or size or other things. Anyway, but those are a lot easier to use. Here's the other side of that. And you can have your MSBs, and you can use, see over on the left there, the DSP 48 slices. This particular thing, it's a 42-bit multiply, and it only used one DSP, which is exactly what you want. And I put the optimum pipeline stages in there at the bottom. I don't know why, but you have to use clock enable. I've never gotten one to work unless you have clock enable and actually wire a true into it. I would think if you didn't have it wired.
Why wouldn't you want to have it?
Well, I just run mine all the time. Why do I need to actually enable it? I mean, I would assume that by default it will be enabled, but I have not. But all I know is from experience, if you don't click the little clock enable and wire a true in, it don't work.
Yeah. So I just assume that input is not there. Like, just make sure that it's checked, but I never could see that I'm checking it.
Oh. Well, when I first started doing this, it wasn't checked by default, and I created a lot of code that didn't work until I figured it out. Anyway, so here's some multiply nodes in action. These are simple scaling. Well, actually, it's a multiply and then an add. This one's taking motion along a line and converting it into motion along two axes. So I'm multiplying the x by a cosine, the y by a sine, and then adding the offsets. Okay. Already mentioned DMA and local FIFOs for arrays, and data transfer from host for that matter. I found out you can get some really fast data transfer from your host over this. However, I have had a problem lately where I can't do simultaneously in and out without them seeming to interfere with each other. And I haven't quite gotten to the bottom of that yet. That could be just an art. Well, I think it's actually a code problem on the RT side. I don't think it's actually the FIFOs.
It is a shared AXI bus on the same as the ARM processor for the FPGA. So it's like a new IP bus. Should be better.
Yeah. It's well, I actually looked at the Zinc 7020 documentation, and in theory, those DMA FIFOs are all independent. It's got a single controller, but there's a thread for each one of the.
It should be independent.
So they should be totally independent. So I'm pretty sure the problem lies actually in my RT code someplace, not there. And given the transfer rates I'm doing, I'm pushing that.
Troubleshooting is kind of hard.
Yeah, I'm pushing that poor little arm.
You need a scope there.
Anyway, one thing I found was kind of interesting. I switched from using a cRIO 9066 to an sbRIO 9627 using a custom I/O board for cost reasons, and I found out that SPI devices on the 9627 daughter board actually take less fabric than the cRIO plugins, and you can get far better performance out of it. I can run megahertz data rates, and I've gotten I think 40 megahertz data rates out of the digital, which you cannot do on a cRIO plugin.
This is just my assumption, but I think it's because there's reserved fabric the FPGA done for the plugin.
Same C-series modules or different?
I was using C-series modules for the 9066. For the 9627, I've got a custom I/O board. Okay. And I'm just running it through digital lines on the 9627.
Digital line.
Yeah.
Well, the C-series modules are just a supply bridge to a module. Well, digital ones are a little bit better, but.
Depends on which digital one you're talking about.
I think they're using.
I think they have a module that goes up to 40 megahertz.
No.
I'm not surprised that.
No, you don't. I can guarantee you that. I've looked.
Yeah.
I think 10 megahertz was the best I could find. Yeah, but I could get 40 megahertz out of basically just by hanging a LVDS chip off the things. Anyway, but for what it's worth, okay, results. I went from 10x to 0.9x, so score.
How many beers?
What? That took me about 3 months, I think.
I said how many beers.
Oh, beers?
You were done with that.
Yeah. Well, there were times I went home and wondered what I was going to do next, and then I'd go read some more stuff and find out more stuff. And anyway, but here it is all into one presentation. Now, I'm not going to say this is all the things you can do to optimize an FPGA. I'm sure there's more.
Well, and one of the things, I was talking to one of the guys that was in the early team of LabVIEW FPGA, and one of the goals is to abstract all of this stuff from us, right? Like the single
cycle loop.
The single cycle loop, they see that almost like a failure because they have to show us something. And I was telling him, yeah, but then when you're trying to make use a most efficient use of the fabric and stuff, you need to do these things.
Right.
Like you do have to know a little bit about how the hardware works. You
it's sort of
cannot
like,
really be
well, I approached this like I approached memory management in LabVIEW back in 2000. You're going to have to do a lot of things that the designers never thought you would have to do. But in the end, it worked. However, then we needed more functionality. Well, I only had 10% left. So what we then did is we took the do less to heart, and I moved the SCurve processing all the way out to the big main controller, and now I'm shoving 100 kilohertz data rates over the Ethernet through the RT into the FPGA, and that took me from 96% to 46%. So now I've got plenty of room to do extra things, which I am doing. Oh, by the way, yeah, that little note on the bottom there. Never, ever, ever wait on an RT FPGA DMA transfer in either direction, whether it's to the host or from the host, because it will totally suck one entire core of the RT processor. It's in some sort of tight loop. Just.
Do you put like a timeout of -1 kind of thing? Or?
Yeah, always. Yeah, don't use a timeout of -1. Always use a timeout of 0. Check however many spots are either open or available, and then you should know your data rate. You can then set a precision timer to come back and hit it again when you've got room.
Poll when you're
yes.
You're expecting data. No.
Poll with precision timers and that'll drop your processor time dramatically.
Do you do the normal or like what I see normal? Read with 0 to check how many items are in the queue, run the FIFO, and then make a decision based on that.
I have done that, but normally what I'm doing is I'm stuffing the what I do is I look to see how many things do I have to put in it, and I've read how many were available last time I was around, and I also know how much time has passed since the last time I was around. Do a quick calculation. If I can fit it in, I do. If I can't, I put a timer in there to wait the exact time I need before I can just then go. And it was, well, I thought that was going to be a lot harder to implement than it was, but it really didn't take much time to do that. RT's got some nice timers stuff, so it wasn't hard at all.
Timers are actually way better than
yeah. What's really funny though is back in it was actually 2000. I needed a precision timer in Windows, and the guy who was, I think it was Darshan Shah, was the original inventor of RT, and he heard me talking to someone about it, and he came over and gave me a Windows call that did it, the high precision timer for Windows that only worked on the new Pentium processors. And that function call is still the heart of RT's precision timer. It's not the same function call, obviously. It's changed dramatically under the hood, but it's still this library call to a precision timer. Anyway, so here's the end result. I'm open for questions. Laser, what?
What's it doing?
Raising metal.
It's it's just a second. It'll be obvious what it's doing. The lasers will fire up. You'll see two lasers melting the surface of the powder in a very highly precision fashion. Those things are pointed to within 10 microns.
Are you moving mirrors?
Yes. Yeah, it's twin lasers, twin galvo scanners, focus and power on the lasers.
Oh, I see.
And it basically, at each layer, we put a thin layer of powder down, and then we draw, and then we melt it. And you can, here's a failed part if anybody wants to look at it. Notice there's a double helix going right up the center of it on the inside.
When you were going through the different optimization steps, did you keep track of like which step made like the most impact on?
Only kind of informally. The big ones were the floating point to integer conversion, and then the math conversion to DSPs.
And I'm always kind of scared of going like all the way to 6 point, because like you just said, it's a lot of work.
It's a lot of work, but I don't think you can really write an FPGA without doing that. You just got to bite the bullet and do it.
Well, unfortunately, most of the people I work with, their algorithms are small. So.
Yes. I mean, the hardcore LabVIEW zealots will tell you, it's just LabVIEW, it's here and that. No, LabVIEW on an FPGA is way different than LabVIEW anyplace else.
That's the discussion I was having with this guy. He's like, they really wanted to make it where it was a higher abstraction, but you can't.
No.
What I've seen is you need to understand how the hardware works.
Yes.
You need to understand registers, flip-flops.
Well, I consider an FPGA actually to be LabVIEW unleashed, because you can put multiple loops and tight loops, everything, and it doesn't hurt anything, because it'll all just execute simultaneously and
It is true parallelism.
yes, it's true parallelism. It's wonderful. The only downside, of course, is you really ought to do it in in fixed point.
So I'm asking if there are any questions from the audience over there. No questions? How many people here are using LabVIEW FPGA?
Okay.
Hopefully you all got access.
I've never actually gone through those configuration pages for the Damien Gray. I've always gotten by with the standard full slides or high throughput divide or 4-wire management.
If you can, good.
It was interesting seeing how many pages there were there and all the different things you can do with it.
Oh yeah, well the DSPs, there's like 6 tabs that, full pages of stuff that you can do. And if you use the Xilinx IP nodes, they condense that down into just a couple of tabs that are a little more manageable.
Right.
A little more easy to document. Yes?
What was that rook? You said it was a failed part.
It is. It's got some curves on it that shouldn't be there. It's kind of distorted.
So
The what?
Why did it happen?
Oh, when we're putting a layer of powder down, well, you notice it's got kind of little spines coming out the bottom. Metal parts, if you're not, you get more and more stress on the part as you build it up, because just think of it from a pure physics point of view. You melt some powder, and then it cools, and now you've got a solid piece of metal. Okay, you put a layer of powder over it, you melt it, now it's hot on the top and it cools, so it's going to try to pretzel. And every successive layer is going to try to curl it up more and more. So the metals we use, that's Inconel. That's a very hard, tough, corrosion-resistant metal. And Inconel will withstand a lot of internal strain. So you have to tie the part down to actually, we've got this big steel base plate about 1 inch thick, and you actually build supports that are literally part of the part welded into the base plate to keep it from warping up when it's first starting. And what happened here was we didn't have the process parameters right, and it was warping more than normal. And the blade that actually lays the powder was made out of polymer. It was basically an O-ring, and so the supports were basically acting like sandpaper and eroding it away. So it got to be, instead of being flat, it was kind of curved, and you can see that curve in the part.
How long did that take to print?
Well, it was one of quite a few other parts. That was probably a day-long build. We can build, we built, the biggest part we did was about yay tall, and it was a day and a half.
with 3D printing, you know, the biggest complaint is strength finish. It's like this metal melting.
Believe it or not, the metal process has been around since the late 80s, early 90s. And commercial machines have been available since about 2001, 2002, I guess. But they're basically the same metal machines they were in 2001 that they're selling today. I can't tell you what we're going to do different. But suffice it to say, we are doing things differently, and that's why I wrote this whole controller in the first place. Because commercial controllers won't allow us to do what we want to do. And but with the FPGA and LabVIEW and then the complete control over the main controller up at the other side, we can change and do things pretty quickly. Like the change from moving the SCurve out of the FPGA all the way up into the main controller, that was a 4-week effort. But so it didn't take long.
Pretty cool.
Yeah. Anyway, there are a couple of things here.
So, any volunteers for presenting next time? Yeah, we already have, so you just need to go collect kudos from everyone. So you get the kudos next time.
Yep.
I have a request.
Yes?
The project provider framework.
You want someone to present?
Who would present that?
Alan, me to do that, Darren Schneider,
He
probably.
suggested it a long time ago.
Do we have a public API?
It is, I think you have to request LabVIEW's network to give you access to it, so it's not like it's not.
It's like half public.
I'm saying
Exactly.
it's a good, I would be interested, is all I'm saying.
No, I think it would be a great help.
To give you guys context, if you don't know what that is, it's the PreProject Dialog window.
So basically, not only that, it's also right-clicking
Right click to the project.
on the project